Z transform of the probability mass function. That is, for a discrete random variables, we have the probability mass function. That is, we have probability that x equal to k. For k, it can take discrete values, but now we are only dealing with the case where it is non-negative integral value. For those things, we can represent this as shorthand notation of pk. For all possible values, discrete k values, it can take. So we now define the Z transform of this sequence of values. So what does that mean? We will represent it using the symbol m, and then as a subscript the random variable x, and it is a Z transform, which means that you are transforming from the k domain to the Z domain. Z is a dummy variable in this transformed domain. So it is defined as k equal to 0 to infinity, because these are the values it can take. It is for a general random variable, so we will let all generally defined for k 0 to infinity. If only certain particular values are allowed, then accordingly it will get. So this is a function of z, and then it is pk z power k. This is how it is defined. So we can write actually this to be nothing but expectation of z power k. Because if you look at expectation of z power x, that's the right way of it. It is expectation of z power x. Z is a transformed random variable. The transform variable, x is the random variable. So if you put expectation of z power x, what does it mean? For each of the value x can take, you give a weightage equal to the probability that value is taken, and then sum it over the entire. That is what it means. So see, right now we are carefully note that we have got an expectation, and the random variable comes on the exponent of this transform variable. But that is not, don't need to trouble you, but once you know the definition, that when you say expectation, for each of the values the random variable can take, you put it in this function and then give the weightage which is equal to the probability that it takes. For example, what is the expectation of g of x? It is in the case of discrete random variable, it is g of x into probability that g of change probability x equal to over all values of k that x can take. This is how we will define. Same manner. So here what will happen? X can take values, non-negative values 0, 1, 2, 3. So it is just P0 is the probability that Z will take a value 0. Plus P1 Z power 1. That's it. That is what this one is. And in a shorter notation we have written it. So this is nothing but a Z transform of the PM, probability mass function. Okay. Well, now we will look at what will be some of the properties of this PGM. We will use the shorter notation probability generating function for this. What is some of the properties of Mx of Z? Mx of Z evaluated at Z equal to 0 will give what value? P naught. That's it. This is not of any interest, just for the sake of what happens, I have put it. Only getting P naught is of no big deal. Mx of z evaluated at z equal to 1 is the sum of all the probabilities. That should equal to 1. So that is the next. Incidentally, I have the attendance. Where is the attendance sheet? Quickly pass it up. I want to correct it by 8:10. 8:10 it should come back. So this is another important simple property. Now, why is it called as the probability generating? Because you want to get the probability that it takes a given value k, you can just use this compact notation function and then extract the probability. So it generates the various probabilities, but you don't need to have a big list. Normally, if you have a PMF of non-negative integer values, it has to be a sequence of lot of values. Okay. You may have a general formula for it. For example, one example of this one is the geometric random variable. Number of trials you have to do to get the success for the first one. It has to be non-negative. It can be 0 cannot of course happen, 1, 2, 3, 4 and so on. And we have a formula for it. That's a compact representation. Sometimes it may not be like that. It may be just sequence of lot of probabilities. Then that's a very difficult, it's not a clumsy one, big array to handle. So instead, if you have a compact formula and then extract the probability whenever you want, it will be used. So you need some compact form, but you should be able to generate probabilities out of it. That is the probability generation. So we will again, how do we get mx of z is P naught plus P1z. In fact, I will put it so I just put terms around the k, which is important. Now let us say we want pk. How do we get it out? But we don't have this form. This actually is a z transform. PGF is a polynomial in Z. Okay? So we have one form of this. We will later on see this form can be something like 1 over 1 minus P plus PZ. This is what will be the formula for mx of Z. Very compact form. But from that view, we can generate any particular probability. Okay. Now, how do we get it? I want this. Somehow I have to remove all these things which are all not related and then take this. To do that, what we can do is we can differentiate this k times. If we differentiate it k times, then what will happen is all terms with power less than k, all powers of z less than k will vanish. So all these are gone. I have from this onwards. This will be there. What will happen to this term? If I differentiate it k times,
there won't be z.
Huh?
There won't be
z.
You can put z is equal to 0. So
No, but what will happen to this term? This term will not have z. But it will be k factorial in p. Okay. But it will not have z. That is also important. What will happen to other terms? No, it will have z. Z here, z squared, it will start from z here. I don't want these also. To do that, I will put z equal to 0. If I put z equal to 0, if I differentiate it k times, I will remove it for everything on this side. If I put z, after that, if I put z equal to 0, I will remove everything here. And I will get hold of this one. But that is, z will not be there. But k factorial in pk will be there. To get pk, I have to divide it by k factorial. Can you take the attendance back? Attendance sheet? Yeah. All of you have signed? So henceforth, beyond 810 I will not, it is up to you to come before that and then sign it. After that I will let you do that. So what we can do is d mx of z by d z power 3. If you do that one, all these will go and then put z equal to 0. These things will be gone. This will be k factorial times pk and this is pk. So to get any particular probability, you have to do this simple trick and you will get the probability. So that is why we call this as the probability generating function, because it can be used to generate probability. Other important properties is, suppose, so what is the mx of z? We will write it as expectation of z power k. We have for any x random variable fx of x, the probability mass function, or this one probability density function in general, and of course the cumulative distribution function. In a similar manner, MGF mx of z is also the function which completely characterizes the random variable, which means that you know that if your PMF or PDF is given, everything you know about the random variable. Similarly, CDF. Now we will tell that MGF is also one such function. If you tell and give me MGF, you don't need anything else. Everything can be found out. Okay. One more thing is, yes. Huh? Z power? No. Yeah, I will tell you. When it will converge, see we can this one. Okay. If you treat Z to be a complex number, for mod z less than 1, it will converge.
As far as I remember in statistical possibles, we learned that it was x of n z power minus the c function. But here the powers of z are positive.
Okay.
I'm just saying that they don't.
Okay, you don't want to interpret it as the way you have been dealing with Z transform, that is different. But this is the definition of PGA. Okay, it may tell that there are other way of defining this one. But this is the definition for PGA. Okay. But the convergence happens when mod Z is less than 1. So, if you have two random variables x and y, which has the same PGF, that is mx of z equal to my of z, then x and y are the same random variables. What do you mean the same random variable? It is they have the same density function. Okay, if one is Bernoulli, another is also Bernoulli. Same parameter, everything is same. That's what it is. It is not, two random variables are not same if they take the same value. That is never. Okay, each one, every realization is random, but the characterization is the same. That is what it means. For example, that is simply because you have mx of z. Okay, if let me say that it is P0, P1, P2 are the probabilities of taking value 0, 1, 2, 3. Okay. P0 plus P1Z plus P2 Z squared and so on. And then Mx of My of Z. The probability that Y taking value 0, 1, 2, 3, I will call it as Q0 plus Q1 Z and so on. These two polynomials are same, then only these two are same. If they are same, then each power, respective powers has to be same. It cannot be different. Clear? Because you can view these polynomials to be, if you have gone through linear algebra, it can be viewed to be a vector in infinite dimensional space of polynomials, and each one z squared, all these things are just eigenfunctions. So from it, they have to be same, which means that PMFs are same, they have the same characteristics. So this is one important. Another thing is expectation of Mx of Z is expectation of Z power x. This is the definition of PGF. So now let us see, you have random variables x1, x2 to xn, and their individual PGF or Mx of M x1 of Z, M x2 of Z, and so on. See, note that, see, Z is a dummy random variable, it's a transform variable, that is what the subscript tells you the random variable. For x1, this is the PGF, x2, this is the PGF, and so on. Now, let us say you have defined the random variable Sn, which is the sum of these random variables. Okay. And let's also assume that these are all independent random variables. Then Sn of Z, if you find, by definition it is expectation of Z power Sn. So and so on. And they are all independent. So what it means is sigma, you should put a multiple sigma for each one into Z power k1, Z power k2, and so on, Z power kn, into probability that x1 is equal to k1, x2 is equal to k2, and so on. This is how we have to put. And because they are all independent, I can write it as factor it. So on, and then take each of them separately. And so on. So this is nothing but mx1 of Z into mx2 of Z. So we can write Sn of Z equal to pi I is equal to 1 to m xi. Hello? I think you are too early for the next lecture. If you want, you can sit for the next lecture. So this is how you can write. What it simply says, if you want, if you have a sum of random variable, the MGF it comes. PGF of the sum of random variables is the, which are all independent, is the product of PGF of the individual random variables. Incidentally, why you keep using the term MGF is, we will later on see moment generating functions, and it is closely related to the probability generating. We will also see something called as the characteristic function, which is, they are all closely related. Now we have seen two things. In particular, we will again do this one. If let us say probability that x I equal to k is the same for all xi's, that is all random variables x1, x2 to xn have the same PM, then which we will call it as, because it is the same for all I, whose PGF I will call it as the MGF of any one of them. We will call it as, we will drop I, because it is the same for all, mx of z. It is mx of z power n, which is quite useful. Now I think we have looked at the definition and how probabilities can be extracted, and this one. Well, now what we will do is, we will do one more thing. We will look at the mx of z is expectation of z power k. If you differentiate it once, what we will get? What again we will write it as sigma pk z power k. If you differentiate it z by 1 time, we get in this one sigma over k pk z into, sorry, k into z power k minus 1. This is what we will get. Actually, you can write it as 0 to infinity, but moment here you write it is actually k varying from 1 to infinity, but I can as well put 0 also, it's not going to harm. And what is this one? Okay, this is something, okay, z power k by itself again a polynomial. Now, if I evaluate this at z equal to 1, then I get k times pk is what we get. And what is this quantity? It is, expectation of x. Sorry, x. Because it is just k times pk. Probability k into probability x equal to k. If you want, that's what it is. What is pk? And that is expectation of x. So if you want the expectation from the PGF, again it is simple, you differentiate it once and set z equal to 1. Now what will happen if you differentiate it twice? See, to get this expectation or mean or the first moment, I will call it, I have to differentiate it once and set z equal to 1. To get the second moment or third moment or kth moment, what do you think would be the formula? What we look for is differentiated k times set z equal to 1, I would get the kth moment. That's what I may probably look for. But let's see what happens. If I put this one here, if we differentiate it twice, I get pk k into k minus 1 into z power k minus 2 into pk. This is how it comes. Now again I can put it. So it is not, k squared is not coming. K into k minus 1 is coming. Or initially I will keep it as k into k. Okay, fine. This is what we are getting. So, in general, if I differentiate it k times, I will not be getting k power, not k times, again n times, I will not be getting k power n, but I will be getting k into k minus 1, k minus 2 and so on. So, that kind of moment is what I will be getting. So, again if you want, I will put it as k into k minus 1 into p. See, we looked at the first moment, second moment and all those things. If it is E of x is the first moment, E of x squared second moment and so on. E of x power k, kth moment and so on. But this is not like that. It is k into k minus 1 and so on. So these also we will call it as moments. But they will call it as factorial moments. So, right now we have been having the following kinds of moments. This is the kth moment. Then we have x minus mu x power k. If you put, wherein we subtract the first moment from the random variable and take the kth power and then take the expectation, that is called as the kth central moment. Now we have a third moment, which is expectation of, it's a factorial moment. What it is? It is k factorial x power, it's not it is the factorial of this. It's not x power k. For that we have to take x into x minus 1. Okay? X into x minus 1 and so on you have to take. K times, that is the kth factorial. It is not x power k, x into x minus 1. To get that one, you have to put k into k minus 1 and so on and then pk and you do like that. They are called as the factorial. So that is what we are getting it.
We can write that as xpk, right?
Huh?
We can write that as xpk. The p is of permutation.
xpk.
Like you get my point, right? As
Yeah,
the
yeah.
expression beginning with xpk, right?
Yeah.
That
Well, now if you want, what we are interested in, this is what we get. Suppose we want the variance, how do we do it? Suppose this one, so I will write it on a compact form. I will write it as m double dash of x sub z. This one. This dash indicates the number of derivatives with respect to z at z equal to 1. Will give you, what it will give you is k square times, will give you, okay, k square this is what it will do. So this is the second moment. This is the first moment, but we know what first moment is actually. First moment is this one, mx. Once differentiation set is equal to 1, you will get the first moment. So in terms of that, I will write is what we get. So what we can do is mx of z double dash at z equal to 1 plus, if I take this to the other end, mx of z single dash at z equal to 1 gives me the second moment. So if you want to get this factorial moment by direct differentiation, but if you are interested in the first moment, second moment, we have to do this step. So it will give you sigma over k squared pk. If you want the variance of x, which is expectation of x squared minus expectation of x, the whole square, that we can write it in terms of the PGF as so this is what you have to write. That is again nothing but whole square. So variance of x can also be found out exclusively. Why I am writing it in a complicated manner? Because everything can be found out exclusively from the PGF. This is the second derivative, z equal to everything at z equal to 1 you have to evaluate. This is the second derivative giving the factorial moment, k squared minus k has come. I don't want that minus k, so I am adding plus k, I get k squared. K squared, that one is the second moment, minus the square of the first moment giving the variance. Okay, can be found out like this. Now what we will do is we will take specific random variables and then look at the PGFs of them. The most simpler one is the Bernoulli random variable. So x is Bernoulli with parameter p means that probability of success of a Bernoulli experiment, or like coin tossing, is p. So x can take two values, 0 or 1, 1 with probability p, 0 with probability 1 minus p, and its PGF is nothing but sigma over all values it can take. This is the formula you have to use. Expectation of x power z, which is sigma over k pk z power x. From this follows, and only thing is you have to substitute this pk values here and then evaluate. So k can be 0, so it is p naught. Okay, k can be 0. When k, if it is 0, then the probability is 1 minus p. Then the corresponding k is 0 into z power 0. When k takes the value 1, the probability is p into z power 1. Yes. Louder. Yeah? Z power 1, z power 0. Mx of z is z power x. That's what I mean. Z power x. Okay. Is pk z power k, and k can take two possible values. You put this one, you get. So that is 1 minus p plus pz. So for Bernoulli random variable, mx of z is equal to, so another way of writing is 1 minus b into z minus 1 minus z. Fine. Now, next random variable is the binomial random variable. Okay. So let us say x binomial with parameter n comma p. What do you mean? You make coin tosses or Bernoulli type n times, probability of success being p, and now ask what is the probability that I will get k successes in n trials. So for that, the x can take value 0 to n maximum. This is what it can take value. So probability that x equal to k, we know it is given by nk p power k into 1 minus p power n minus k. For that, given the PMF, if we find the PGF, now it should be trivial for you to do one-time differentiation and substitute z equal to 1 and get the expectation, all these things. Okay? If you differentiate it once with respect to z, these goes away, you will get here p, and then substitute z equal to 1, which is now, which will give you p. That is the expectation of the Bernoulli random variable. All these are very this one. Variance can also be, you can find out, will be variance will be equal to PQ for Bernoulli. That can also be, you can find out using from this formula. So here what will happen? Sigma k is equal to 0 to n k p power k into 1 minus p power n minus k. This is the probability pk. Now z power k I have to put. So sigma pk z power k. Pk is this one, z power k you have to put. So nk. Now what we will do? These are all same power. Repeat. So now we can now it is an expansion. Again, same a binomial expansion. Is nothing but 1 minus p plus pz power n. because 1 minus p, pz power n is the expansion. You can write it like this. See, now what will happen is, see, for a Bernoulli random variable, MGF, PGF is 1 minus p plus pz. Okay? For a binomial random variable with n Bernoulli trials, it is the nth power of the Bernoulli, PGF of the Bernoulli random variable. It should be obvious because what is Bernoulli with n trials? Yes, it is Sn is equal to x1 plus x2 plus xn, where each one is a Bernoulli trial and therefore its PGF is known. If you want the PGF of this, it is on same identical PMF. So it has to be nth power. That is what we are getting. So therefore m Sn of z is equal to mx of z power n, and that is why we are getting as power n you are getting. So the next one is geometric random variable. Okay, but what we will do is we will take modified geometric random variable just to make the formula simpler, but immediately we can generalize it to geometric random variable. What is this one? This is the number of failures before the first success. In a sequence of Bernoulli trials. And we know the formula for that. Probability that x equal to k means, that is what we are telling, there has to be k failures before the first success occurs. Where it's each one is a Bernoulli trial with success probability p, failure probability q. So it has to be 1 minus p power k, because k failures have to, and then it has to be a success, then only it will stop at k. If you call this as q, it is q power k into p. So this is the PGF of the modified geometric random variable. So mx of z for this one is zero to infinity. There can be zero failures before the first success. First itself can be okay. So here it's a qz power k, q is less than 1. If you take the modulus of z, this will converge if for only for those z where whose magnitude is less than 1. So for that it will be p divided by 1 minus 2z. Now, if it were without modification, the other one means only thing is I will add here q power k minus 1 into p if it were the geometric random variable without modification, which is the number of trials before I get the first success, means k minus 1 failures and then first one success. It is q power k minus 1 into p. But this form is good because I can club the q and both of them together and write it. So for that, what I have to do to get this one, I will multiply by 1q and divided by 1q. Then only thing is, if I divide it by 1q, then it will be similar to this one. For a geometric random variable. Then the only thing is q by p into 1 over 1 minus qz is the only difference that will happen if we deal with the geometric random variable. This will be the MGF, PGF of the geometric random variable. Now we will look at next modified negative binomial distribution. What is negative binomial distribution? That is the number of trials you have to conduct to get the kth success is the negative binomial. Why? Because you are not asking the other way. You conduct n trials, how many probability to get k success? If you ask that kind of a straightforward question, it is a binomial distribution. Negative binomial means you fix the number of success and ask the number of trials you need to get that success. Number of trials needed to get the kth success is negative binomial. Now again it is modified because you concentrate on failures. That is number of failures before getting kth success. Let us say rth success. Okay. So this is what we will see we will get. Again what we can do is we can write down the PGF, PMF for this and then substitute it and get it here. But instead of doing that one, what is this one? This will be the sum of or modified geometric random variable. Because number of failures before you get rth success means you have to conduct trial number of failures before you get the first success. After that the process renews itself. Again you have to conduct trials to get the second success and so on. So it will be, each one will be a modified geometric random variable. R times you have to do. So it will be a sum of them. They are all independent. Each trial by itself is independent. So the MGF of this one will be the power of rth power of this will be, I will put, this will be modified negative binomial distribution. This will be the modified geometric distribution of z power r. To differentiate x, I am using this one to differentiate what x we are looking at. So what will be that one? That will be nothing but p divided by 1 minus qz power r. Just take the rth power out. Okay. Then the Poisson random variable. Here probability x equal to k of lambda. Probability x equal to k is sigma, k is e power of minus lambda, lambda power k by k factorial. So you will get mx of z this is the pk z power k. E power of minus lambda, we will take it outside by okay, and then sigma lambda z power k by k factorial. What is this one? This is e power of plus lambda z. Plus lambda z. K minus 1 is what we are doing. Okay.
Sir, lambda z, right?
Lambda?
Lambda z to the power is by k factorial.
Huh?
That will be e to the power lambda z in the second last step. Right step.
This is e power of minus lambda z power k by k factorial. Lambda z, sorry. Z dash to z. Because it's a function of z. So that's it. So you can now look at differentiating once z equal to get the mean, whether you are getting the expectation variance of Poisson, you can try this one. So we will stop at this.